So today's topic of discussion is controllability of our system, of our linear, and like previous discussion, here also we'll consider with time varying system, and obviously time invariant system will be means later on can be treated as a special case of time varying system where variation with respect to time remains constant. Before I go to theoretical discussion, just let me give you a brief intro of the subject, what it's all about, this controllability. If you take a balanced network of balanced, say this is balanced network, this one is your. Now let us consider two input configuration. One is this one and another one is this one. So you can understand that if we apply any voltage across, suppose we are having an initially relaxed capacitor and our goal is to change the capacitor state value. Okay, let us consider that we have a capacitor that is having some say some 20-volt capacitor we have, right? And the capacitor, once we put that capacitor there, means 20 farad initial charge is 20 farad and capacitor value is 1, sorry, I again made a mistake, 20 coulomb charge is there and the capacitor value is 1 farad and therefore you are having 20 volt across your capacitor plate. Fine. Now you just place it in this balanced bridge circuit and then what you are looking for, you are actually looking for uh, means an input that can like instantaneously make your capacitor voltage zero. However, there is no bound on that input magnitude. Means any magnitude can, even if you can go to 1 megavolt, 1 kilovolt, 1 teravolt, whatever you want, you just apply it. But instantaneously you have to make this capacitor voltage. So now if we consider the two port or rather pair of port terminals that gives us a port, that is the red one, then you can see that for the red one we can change the capacitor voltage within a very short time. Like if we have to make it zero, we can just short it, and if we short and if we consider C is an ideal capacitor, instantaneously it will become zero, right? Now if you consider the other case, suppose if you take blue, then whatever voltage you apply across the that blue, or better to say cyan color terminals, it will not be able to affect your capacitor voltage or capacitor current. The capacitor voltage or capacitor current may go to zero or any other value it may assume depending on its nature of the circuit and all other things. But one thing, if you apply the voltage across your cyan terminals, the capacitor will become kind of it will not able to realize any controlling effect, or it will become free from your control action, and thereby the two cyan terminals will make the system, if you choose the cyan terminal, that will make our system uncontrollable. Do remember this A matrix and B matrix, what we write in equation 1, that is x dot is equal to xt plus bt ut. So clearly it is someone that is B, that is responsible for transferring the effect of input to our state variables, and that is why it is known as input distribution matrix, the matrix that distribute your input effect on the rate of change of all the state variables, right? Now see one interesting, very interesting things here, that if you select the cyan color terminals, you will have an equation of system, and if you select the red terminals, you will have a different equation of system. Now see that this is the basic idea of controllability. Now obviously in every case you cannot start from your physical system and analyze that whether your system is a controllable or uncontrollable, and even knowing your system state matrix won't help. So how can we combat that? The answer is that it's very simple, that we need some mathematical tools. So what are the tools we can have? Or like the previous chapters, we will study theorems, and from that theorems we will try to say that system is controllable or not. So first definition, this equation 1 is controllable within, since we are taking a time varying system, we are taking a closed interval of time. If given any initial state xt naught is equal to x naught, there exists a continuous input signal ut such that the corresponding of equation 1 satisfies xtf is equal to 0, right? xtf is equal to 0. So see, this one is actually trying to say what I just discussed. It is just giving you a mathematical representation of what I just described to you. Now we will look for a theorem. Before we go to that theorem, let me tell you a few things, that our continuity requirement of the input signal is constant, and means it is like in accordance with our default technical setting. So like we can have means there is no harm if you apply smoother input, like means if you think about having a disjoint input and then you try to do analysis, then things will become a bit more complicated, right? Now see, so this equation 1 is called controllable if for a given time instance and given any arbitrary initial state. Unlike that, means here it is not means the initial state must not be within a limit. It can be anywhere, any value, any arbitrary large value it can take. There exists a continuous input signal ut such that corresponding one satisfies xtf, that is the time limit. Do note that this, as I have written, it is in a form of a closed set. It automatically implies that you are your means TF is finite. TF, even if it is infinitely large, if it is very large, but it is not infinite, it is finite. That is why I could write it in this closed equation form. Now see what this theorem states. Like everywhere, we would like to go for theorem. And before I go to theorem, I would like to discuss one thing, that the continuity requirement of this input signal is in accordance with our default technical understanding. Uh, like means in reality we get a much smoother input signal to means drive the state to zero. Means it is not that you need a very harsh discontinuous input signal to make it zero. Means from reality, means real perspective I am telling you. Then uh, and another thing in particular, as we have mentioned, it is within this band T0 to TF. It is also not required that once you cross TF, means T greater than TF, you need to ensure that your means it is not that once it reach there and it will means your control input will ensure that obviously that X means if the origin is your equilibrium point, and if you do not disturb it after TF, it will remain there forever. But it is not always the means the not requirement. Now here what we will do is that we will study a few theorem. What this theorem state, the equation 1 is controllable on T0 comma Tf if and only if this is a typical form. Please note this one. This one we use to define our controllability Gramian. This is known as controllability Gramian, as shown in equation 2. This controllability Gramian is invertible. Now we will prove it in two ways. First, we will see that if we assume controllability Gramian is invertible, then it in turn implies that system is controllable, and then we will try to prove it by contradiction. So here what we are writing, that suppose Wt0 comma Tf is controllable, then given any vector, this x0 is any arbitrary vector of n dimensional arbitrary vector, what we can have, we can means define input signal ut is equal to minus b transpose t phi t t0 comma t w inverse, because we have assumed w is invertible, w inverse t0 comma tf x naught within that band t0 to tf. And obviously our input signal values outside the specific interval, means we are not interested to consider the input value outside that specific interval, and within that interval, within that 3, if we consider t0 to tf, since within that interval your w is continuous, means w inverse is invertible, and also the other parties are continuous, so you can see that ut will become continuous in some sense. So if input signal, that is ut that we have defined using equation 3, is continuous, then the corresponding solution of our equation 1 x dot is equal to that at xt plus bt ut, and the y also, but now we are only focusing on x dot t is equal to at xt plus bt ut. That one with your xt naught is equal to x naught, we can write it like x tf in that common solution form. This one you must have noticed in from our earlier video, that what would be the final value of state. Here we need to define a state transition from x naught to xf, sorry, means t naught to tf, and whatever be the corresponding value. So it is xtf, we can write it in this way. Now see, here we have this u alpha, u sigma. This u sigma we will replace by this 3, what we have in our equation number 3. Then what we will have? We will have this one. For our means better means it should be like clearly noticeable. That is why I made it means with, I wrote it with a different color. Now using the composition property of our phi, that is our very own phi, what further we can do? We can do one thing, that we can write from that composition property, we can write this is going to be your 0. Now think about one thing that is very important, like if you consider the first means a few questions that we must understand, that how come we can take w inverse out of this integration, because w by its construction, it is already means it is a kind of means once you do an integration and then you get w. So w is a kind of value you will get out of one integration. So means here means not a value, like a constant matrix whose entries you will get by that integration. So once that integration is done, then there is no point of means making it means for two terminal values, because you are carrying out a definite integral for finding out w, its value is fixed, when its entries are fixed. So for another state transition, your w is not going to change. So that is why we can take w out of this, means if you notice, then t naught and ta both are constant. So for this given case, so we can take w out of this game and have our these two things. Now what by composition, what I am trying to say, what we did this manipulation. Here this phi tf comma sigma, we broke it like phi tf comma t naught and phi t naught comma sigma. So that you can see here, phi tf comma t naught, again this is a constant thing taken out of that, and the remaining. Now whatever we are having here, interestingly, that is our w. This thing what we are having here is our w. Only thing is that previously the integration variable was t, now it is sigma, but the result of integration will be w, and that will be w t naught comma tf. So that will become, total become 1. So means identity matrix, and therefore these two will cancel out and give you 0. Now, if this gives you 0, then the we can prove that xtf uh, means we can make xtf is equal to 0. That is the statement what we claimed in our controllable to prove the system is controllable. That is the statement we made at the very beginning. Now, uh, another thing we can show using that our favorite strategy, reverse implication. So what we can do is that let us consider that the state equation, that is x dot t is equal to atxt plus btut. Just let me check whether it's recording or not. Yeah, atxt plus btut, that itself is controllable. Okay, but your w is not invertible. So if we obtain a contradiction, now we will proceed. First we assume W is invertible, then that means if we just do some manipulation, we get XTF can be made 0 with only if we can ensure Gramian is invertible. Now we are considering that system is controllable. That means any given instance we can figure out an input that can drive any arbitrary state to 0, but uh, our WT naught comma TF is not invertible. One thing I would like to mention here, that quite often it is said that controllable to means the system is controllable to origin, because this XTF is origin. So controllable to origin, that also becomes valid when we will consider non-linear case, but that is quite a different scenario and I don't want to make things more complicated. So let us keep it simple. We are looking for controllability and this test. So what we will have here is that the like if it is not invertible, there exists a vector xa. There exists a vector xa. Xa belongs to Rn such that we can have 0 is equal to xa transpose wt naught comma tf x. Why? Because w is not invertible. That means w is having means w can give us 0, right? Means for some particular combination w determinant is 0. Now if that is the case, then that we can express it in this way, that just by expressing w. Now if you consider the means this inside one, then that can be written like it is something that the integrand means, by the term integrand I am trying to mentioning this one. This is our integrand. But look at them, they are appearing as a quadratic function. And one thing that is quite certain, that they are non-negative and continuous function. So it follows that they must be is equal to 0, like xa uh, t, this must be is equal to 0. The integrand, this is our integrand. This integrand is non-negative and your non-negative and also continuous. Therefore, what we can have here is that x a transpose phi t naught comma t bt is equal to 0. This is equation 5. Since the state equation is controllable on t naught comma ta, choosing our x naught is equal to x a, obviously we can think about there exists a continuous input ut such that 0 is equal to, we can write it in this form, and that implies xa is equal to, means from where we are getting this confidence that there exists a continuous input, because now this is our second part of the proof where we are trying to prove it by contradiction. We have already assumed that our system is controllable. So once you assume your system is controllable, then basically you are guaranteed, means you are ensuring that they are a good, means there will always be an input that can make your state 0. Like this guy can be treated as xtf. So, and how you can reach there from xtf? This is the common equations. Sorry, I made a mistake here. It must be ta. Huh. So basically this becomes a continuous case. Now see what we can write here, that xa becomes our this. Now see that we can, yes, due to this we can write it like tf comma t naught. Okay, so what we get it from this xa, that becomes this one. Now if we multiply both sides by x transpose a to make it quadratic, then what we will get? We will get xa transpose xa is equal to minus integration running from t naught to tf xa transpose this total thing, and that should be is equal to 0. Now this contradicts our very first statement that we have something, an arbitrary vector xa that is not is equal to 0. Means we assume, we start here wt naught comma tf is not invertible, fine. Then also we took another assumption that xa is 0, means non-zero vector, means xa is not located at origin, it is somewhere else. So what final conclusion we got, that xa cannot be any other thing than 0. When if you consider wt naught comma tf is like not invertible, and still you are claiming you are having means controllable system for which any arbitrary state can be driven to your origin, that is a false statement. Means two contradicting statement. So this is kind of both means your necessary and sufficient condition to ensure your system is stable. Now, what do you think about this W? Let me once again go back to the W, the structure of W. It's not Bablu, it's W. I'm talking about. Somewhere I must have defined it. Yeah. So, what do you think about W? This W is is it can it be sign definite? Can it be symmetric? Can it be positive semi-definite? What do you think? Now, by its structure, we can say it is going to be a symmetric one. And also, the way we have designed it, it is going to be a positive semi-definite. But what we can show, that is a very means means important observation, that until unless your W is a positive definite, you cannot means ensure the system is your system is controllable. Now, how can we explain this in terms of our means intuitively we can get it. See, if you take one side like either phi t naught comma t bt or b transpose t phi t naught comma t, what are they? They are someone who governs your zero state solution. If you consider the complete state solution, then you will find one is zero input that we are dealing with while discussing internal stability, and another one is zero state. So this one is due to zero state. Now while you are trying to drive one state value to some another value, then obviously if your zero state becomes incompetent or means it becomes zero sometimes, then you will not be able to drive it, because your means together your zero state means zero input solution will be there and zero state solution will be there, and if you add these two, then you will get to zero. So that is very clear, and clear idea you must have that you are having that one part that is okay. You are having some whether state transition takes place or not, that is also a different thing. If suppose our system is not stable, but still it can be controllable, and by virtue of your external effort, you can drive it to zero. Means if it is not suppose the system is not stable and it is like the means zero means what? It must converge to means show some exponential nature if your system is exponentially stable. So it is not required that your system must be exponentially stable. It can be anything, but still cannot be. We can have a controllable system. So these things you should not miss. These subtle things you should keep it in your mind. Those are the important things that are going to help you. Another thing is that by definition, if you go to calculate W and then check its invertibility, then that is not going to a very uh, convenient one, and no one would be happy to do so. So how we can circumvent this? Now, this one we will try to do. Uh, One thing what we can do is that we can assume the smoothness properties are stronger than continuity for the coefficient matrix like your A, B, and the Gravian condition in our this theorem leads to a sufficient condition that is easier to check, like means we are like continuity, and also we are considering it is smooth enough. Well, what I am trying to mean that you will be able to understand when you will try to solve that worksheet problem. Now, another thing what is very important here that I should not skip, I should mention it. And yeah, this one is basically giving you something that is uh, this equation actually corresponds to a case of linear dependence condition on the rows of phi. It's obviously xat you cannot do anything. The last two terms, this I'm trying to mention, these two terms are having some linear dependency. So from that, if we trace back, what we understand that controllability criteria is having its root in your linear independence of your means that the roots must means it is the fundamental understanding is that these two matrices must have independent uh, rows or independent columns. That is the most important thing here. Now, let us go for another advanced definition. Uh, Corresponding to equation 1, what we can see that say equation 1 is and subject to existence and continuity of the derivative of this Gramian. Indicated derivative means derivative of this Gramian. Let us define a sequence of n cross m matrix functions by we are defining n cross m matrix function by k naught t is equal to bt. Then kjt is becoming what? Kjt is minus at kj minus 1 t plus kj dot minus 1 t. We can easily show or easily prove by means of induction that this this d this partial differentiation of phi t comma alpha sigma b sigma will lead us to this case, right? So will lead us to this case. Now, here specifically the means this claim obviously holds for j is equal to 0. Now with capital J non-negative integer, suppose we have this, right? Then using this means inductive property or inductive hypothesis, we can write that this one is like k j alpha d dt phi t comma alpha k j alpha, sorry, again and again I am telling sigma alpha, pardon me, it is sigma. Even if I utter the word alpha, you should understand that sir is trying to mention it is sigma, not alpha, right? And then what you will get further, that once you do it, that will lead us to this state. Because partial differentiation simple, if you do d sigma of phi t comma sigma, then you will get phi t comma sigma a sigma and kj sigma plus this one, and that finally lead you to where? That finally lead you to phi t comma sigma kj plus 1 sigma. So that you can understand that how this differentiation and what we try to define from this state is corroborating, or means this definition is corroborating whatever we are writing here. It's correct. Now if we try to understand one simple thing, that at t means sigma is equal to t, we can have a very simple interpretation that kjt is equal to dj. Here sigma is equal to t. Like if we need to evaluate it at any certain time point t naught or t, we can do it. Now with this definition, let us consider a theorem. Suppose there exists q, that is a positive integer, such that we have t belongs to t naught comma ta, and bt is q times continuously differentiable. Like you can represent this in this way, like if b is something like you can write that all these b's are all b I comma j, they belongs to CQ. Here this is not your complex C. This is complex system, or but this one defines a function that is q times differentiable. Like if you consider sine theta, that is c infinity, means it is infinite time differentiable, right? So CQ is a function that is q times differentiable. And our AT is another function that is q minus 1 times continuously differentiable. then the linear state equation is controllable on t naught comma ta for some tc belongs to t naught comma ta if we can show that the way we have defined rank means sorry k k in that our just a few minutes back we defined k. So from that k, if we can show that rank of k naught tc, k1 tc, kq tc is equal to n, then it is the case. Now suppose for some tc belongs to t naught comma tf, the rank condition holds. And in addition, let us to set up means again we would like to go for proof by contradiction argument. Suppose the state equation is not controllable on t naught comma ta and there exists a non-zero then this is not invertible and there exists a non-zero n cross 1 vector xa such that we are having xa phi t naught comma t bt is equal to 0. So while t belongs to t naught comma tf. Now what we are trying to show that xb be the non-zero vector such that we are having xb is equal to phi t naught comma tc xa. Why so? Because we are now we are discussing everything for a particular time point tc, means we are considering point-wise time point-wise controllability. So that should be and while considering the time point-wise controllability, while we are doing all this just to means bypass the calculation of our w. The w can be bypassed if we can consider and can do this kind of things like once because if you compare the calculation of k, that is much more simpler than carrying out an integration of w. So one thing only that you need to calculate the invertibility of such matrix comprises k for all the points within that one, or better to say have to check that within that interval throughout the interval that matrix must be invertible, but that is not a very big deal. If you see its structure, then it is somewhat simpler. The way we have defined our k naught and kj, they are somewhat simpler than what we are trying to define. Now here what this is clearly well, now see that, so here we are assuming that we are having one xb non-zero vector xb is equal to t naught comma tc such that what we are having here that xb phi tc comma t bt is equal to 0, where your t belongs to t naught comma tf, means from any time we start and then when we end up at tc we are getting this value. Now in particular that T is equal to Tc, this gives us what? Xb, what is this one? This phi Tc Bt, we can write it like right. Now if this xb transpose k naught t is equal to dc, now if we further differentiate 10 with respect to t, then 10 will give you us what? Then 10 will give us uh, sorry 10 will give us xb phi tc comma t k1t is equal to 0. See the structure of the equation 10. If we see and if we differentiate, obviously what we will get, this one is constant x at t, so keep it aside, and what you will have, uh, in one instance you will have this phi t naught comma t bt, and in another instance you will have this dot phi t naught comma t bt. Then applying this property, what we will get finally you will get, this will become xb phi tc comma t k1 t is equal to 0 for all t that belongs to t naught comma t, from which we can write xb transpose k1 tc is equal to 0. So if you continue in this way, then what we will get? We will get this is equal to xb kj tc is equal to 0. That is true. Now therefore it gives us means, if this is the case, then what we can say, that further if we elaborate it, xb transpose k naught tc k1 tc kq tc is equal to 0, right? And this one contradicts the linear independence of our n rows implied by the rank condition that we have in some previous equation, probably equation 9. Yes, this is means contradicting with this one, because if it is n, see here we have already assumed somewhere, just a minute, letting xb be the non-zero vector. So if this becomes 0, then it clearly indicates that xb cannot be 0, rather these guys must be 0. But if they are 0, then how come you are getting that rank condition fulfilled? So it is not the case. Therefore the state equation is controllable on t naught comma ta. Now in our next video we will discuss about our time invariance and the like observability of a system. Just a minute, somebody again